Everyone is doing well on this bright and chilly Friday morning. Just thought I'd start with a few reminders. The RFQ response is due Sunday at 11:59. If you have any questions about that, feel free to email me, and happy to answer those. The participation question will open shortly after class, and it is also due on Sunday. This will be an easy one. It will not require you to contact Teams. It should be an easy answer, more of a touch-based type question. Homework 2 is I moved from Monday to Wednesday to give you a little more time, and hopefully we'll be able to help you with that, or that'll help. And we'll continue flocculation, coagulation, flocculation, rapid mixing, etc. Through hoping to finish it on Tuesday. So I'm going to start with a poll. And so the question I am asking you is which is likely to be the most effective coagulant? And I've given you 3 choices: sodium chloride, hydrated lime, or alum. And I've given you the chemical formula for each of those. And assume that they're added in the exact same concentration. And the majority of you said that alum would be the most effective coagulant, with hydrated lime second, and then sodium chloride third. So let's just go back and look at charge of 1. So sodium chloride would have a charge of 1. Calcium hydroxide, the calcium has a charge of 2+, and the alum has a charge of 3+. So what you can see here is that assuming that the concentration is constant, what's going to happen is these are considered what we call indifferent electrolytes. So they only interact by compression of the double layer. So what you see is that sodium is less effective at compressing the double layer. Calcium would be more effective, and alum, or the aluminum, would be the most effective. So the aluminum would be the most effective coagulant. So hopefully that helps with that. And we can see that in this figure also. What you see here is we're plotting residual turbidity versus concentration. And if we just look at the 50% turbidity line, what you see here is that in order to achieve 50% removal of turbidity using sodium, we would need about 0.1, and this is molar concentrations. My toolbar hides the concentration. For calcium here, we're right in this range here. So we're talking about maybe 5 times 10 to the minus 3 molar. And then for aluminum, we're right in this range here. So maybe about 2 times 10 to the minus 4 molar. So you can see we need much less aluminum than we did calcium and then sodium. And if you remember, perhaps, that the critical coagulant concentration is a function of 1 over z to the 6th. Okay, so that was the Schultz-Hardy rule, is what it's referred to as. And you can see that charge plays a very, very significant role on that critical coagulant concentration. And you can see that here. Now, this is dodecyl ammonium, and it behaves differently. Dodecyl ammonium is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is dodecyl ammonium. It is a long chain, a carbon, so it's C12. This carbon chain here is hydrophobic. It does not want to be in solution. This, on the other hand, is a charged species, and it is hydrophilic and wants to be in the aqueous solution. So basically what happens is you form so if we have our charged particle, the ammonia end will associate with the negatively charged particle, so it will complex there, leaving these long chain species, and they tend to help ensure that the coagulant wants to precipitate, that wants to come out of solution. The problem is these hydrophobic ends tend to want to interact with each other, so if you add too much of it, then notice here you end up with a positively charged, and this is not to scale, but you end up with a positively charged particle. And what you see here is what we call charge reversal. So your negatively charged particle becomes a positively charged particle with these ammonium ends kind of sticking out of the particle. And those are in the solution, and that tends to, now you've got positively charged and your particles will repel again. Typically with these, where you have indifferent electrolytes, as I mentioned, that means that they're interacting by compression of the double layer. You can think of it that way. You typically don't get charge reversal, or you have to have very high concentrations. With aluminum, you'll see in some of the figures, you actually can get resolubilization depending on the dosage. So you can, sodium behaves as an indifferent electrolyte, aluminum to lesser extent. Here, okay, you can ask the question, what we have is a freshwater river, and the question is, why do the particles of clay in a freshwater river settle as they mix with the saline water in the estuary? So why might that be the case? I'll give you a chance to think about that. So what's happening here?
So when it hits like the salt, does it just like coagulate?
Exactly. So you've got a high concentration of salt solution in the estuary, typically about 20,000 milligrams per liter, so about 20 grams per liter. So you're looking at molar concentrations of salt in that fresh water. So as the clay hits that fresh water, what you're doing is essentially adding sodium chloride, compress the double layer, and you get coagulation. So that's why in the image,
situation where if you hold it there,
look, in the image here, you see that the water becomes clearer. So what's happening is you're getting coagulation right in this region here. And those particles can flocculate, or if the water is quiescent enough, there's some mixing, so they mix, and then they settle out. Basically, this is the way a delta is formed in a river as that river hits the estuary. And I've just basically said what's on this slide. And you can see here, and we've talked about this. So this is the situation in the freshwater where the repulsive forces predominate and you have a stable colloidal suspension. And then when that fresh water hits the saline water, you get compression of the double layer and you form an unstable colloidal suspension. And we can use this in an engineering system to treat waters. Okay. I'm not going to talk a lot about Zeta potential, but I want you to know that this exists. And basically, Zeta potential is a way that we measure, what we do is we measure the movement of a charged particle in an electric field. So you take a water sample, you apply a charge, you measure the movement of that particle towards the pole of opposite charge. And based on that, you can then assess how effective the coagulant is. So you're really assessing and looking at that 0 point of charge. So where are you neutralizing the charged surface? So you can get a better sense of the mechanism, essentially, by which the coagulant is working. Now, we've talked predominantly about compression of the double layer. I mentioned adsorption and charge neutralization, which really is what happens with the dodecylammonium. Now, you can also get adsorption and what we call interparticle bridging, and that is shown here in this reaction right here. So basically, you can think about this as essentially your negatively charged colloid, and we have something like dodecylammonium, and what happens is these two hydrophobic ends interact and you form a larger particle as shown here. Now, the challenge with this is you have to be, these doses of these organic polymers are very, very sensitive, or coagulation is very, very sensitive to the dosage. You can, if you're not careful, you can see here we've got this particle, and it can essentially, the long chain bends, interacts with the particle, and you're not getting any interaction with another particle, and you simply just restabilize the particle. You can add too much of it, and you can see you've got all these other ends, and now you restabilize your particle, or you rupture, in this case, you rupture the flock. So you form the flock here. It should settle, but in the flocculation system, if your mixing is too intense, you break apart the particles and now you restabilize it. So those are just some of the mechanisms that we have to be very careful of. So when we are operating a coagulation system, we talked about rapid mixing. So we want to ensure that the coagulant is dispersed throughout the solution. We then said that we have a flocculation basin. So we need to be very careful here, because if we have too intense mixing, we end up with this situation right here, where we actually rupture the particles, and we restabilize the colloid. If we don't have sufficient mixing, then those particles don't come in contact with one another, so therefore they can't combine and become large enough. And tell it's Friday morning because the landscapers are here. I apologize. And then the last one is a meshment in a precipitate. So here we're actually adding so much coagulant that we exceed the solubility. And what we're actually doing is precipitating. So basically the flock that we're trying to remove, or the particles that we're trying to remove become enmeshed or encased within this particulate. So here we exceed the solubility. We're actually exceeding the solubility of the coagulant, and our particles that we're trying to remove become encased within that particle, within that precipitate. So in terms of coagulant properties, what we want from a coagulant is we want something that is non-toxic. Remember, we're looking at producing water that is palatable and potable. If we add a coagulant that's toxic, the water isn't going to be potable. We also want a coagulant that is relatively inexpensive. One of the problems with a lot of the organic polymers are they're very, very expensive. And so that increases the cost of producing water. We also want something that is relatively insoluble at neutral pH range. We don't want high concentrations of either calcium that's going to contribute to hardness or aluminum in our treated water. Or in the case of where we add iron, we don't want high concentrations of iron in our water. You know the problem with that at MSU. And then typically we want a high charge density, and that was because of that Schultz-Hardy rule. So the aluminum is much more effective than calcium or sodium. Some of the common coagulants are listed here. These include alum. Alum is most common in the US is alum, ferric chloride, and now polyaluminum chloride, and you can see it here. It's a complex formula. It changes with manufacturer formulation, but these are typically the most common. And then where we add polyelectrolytes, these are most often added as a coagulant aid. So where we're trying to improve coagulation beyond what we can achieve with either one of these coagulants. One of the challenges of these coagulants is that they tend to be effective only in a fairly narrow range. So alum is typically most effective in a pH range from about 5.5 to 7.7. Ferric chloride is more effective at a higher pH, or more effective over a wider range, so it's from 5 to about 8.5. And then this polyaluminum chloride is effective over an even wider range. So you can see why polyaluminum chloride is now one of the most common coagulants used in drinking water systems because it is so effective over such a wide pH range. These organic polymers, these include the dodecylammonium that I mentioned before. So you've got a long chain carbon molecule and then a charged end. And as I've mentioned, these are typically used, if they're going to be used, they'll be used as coagulant aids. They also may be used as filter aids, basically to try and improve the filtration, so achieving a more clarified solution, so you can actually get coagulation occurring in the filter. And sludge conditioning, where we're trying to improve the properties of the sludge so that that sludge dewaters more effectively. Because what we don't want to do with sludge is we don't want to be transporting a large quantity of water to the ultimate disposal site because of the cost of that. And this is just some of the typical organic polymers. They can be anionic, they can be non-ionic, they can be cationic. In flint, they actually added anionic and cationic polymers. They were having trouble achieving efficient settling after their lime soda ash softening process. So they actually, during the entire process in Flint that they were operating and treating Flint River water, they kept changing the concentrations of the anionic and cationic polymers. It's one of the few places where I have ever seen where anionic and cationic polymers are both added. But it was, as I've said multiple times when I talk about Flint, essentially what they did was they operated a pilot plant at about 15 to 20 million gallons per day, because they were struggling the entire time to maintain efficient operation. This is jar test apparatus. I'm going to skip over much of this, and we'll talk more on Tuesday. On Tuesday in tutorial, we'll look at some lab data. We'll look at basically the lab that we would have done if we were in person. We would have done as a demo. But Joseph, the lab manager, went into the lab this summer, recorded I don't know how many hours of data, which I then edited down to about 10 minutes or so. So we will look at that. We'll look at a comparison between alum and ferric flock so that you have some better sense of, when we're talking about flock, what that means, what is a jar test, how do we use that data in a process setting. So I'm going to skip over these next slides, and we'll talk much more about those on Tuesday. So we have a situation where we have a surface water treatment plant. It is operating at a flow rate of 0.5 cubic meters per second. It is dosing alum at the optimum dose that was determined in a jar test, and we're going to assume that is 12.5 milligrams per liter. So it's adding the aluminum sulfate. We'll assume that no other chemicals are being added, and we have a raw water suspended solids concentration of 87 milligrams per liter. This is extremely high, but perhaps there was a major storm event and that mixed up the sediments, and we now have this river water that we have to treat with a very high suspended solids concentration. And we want an effluent suspended solids concentration of 0.7 milligrams per liter. Just thinking about this. Okay, so we would have, just in terms of the plant, we would have some sort of screening. What's the next unit process? we would have. It's a process where we want to ensure that our coagulant is evenly dispersed in the water. Exactly. So we have rapid mix, also called flash mixing. And from there, we go into what unit process. Okay, so in the next unit process, what we want to do is we want to slowly mix to allow these particles to come together and to aggregate. So we want to produce bigger particles. Coagulation. So we've produced bigger particles. Now, what's the next process? Sedimentation. That's where we're going to produce the sludge. And we have the clarified effluent. And typically that will go then onto filtration. And here, disinfection, storage, and pumping. So just to give you a sense of kind of how this all fits together. So we have a situation here where we have a flow rate of 0.5 cubic meters per second. That's our water flow rate. We have a coagulant dose of 2.5 milligrams per liter. We have an initial suspended solids of 87 milligrams per liter. And we have an effluent suspended solids concentration of 0.7 milligrams per liter. So let's go back and look at our, we have rapid mix. So we're adding the coagulant. Okay. We have flocculation. We have sedimentation. And we have, I'm going to call that's our effluent to the filters. So really when we're thinking about this, if I'm going to draw my system boundary and I wanted to do a mass balance, I'm going to draw my system boundary across this entire system. So I'm actually looking at the water in, the coagulant in, the effluent out, and the sludge that I'm producing. Okay. The lines from the rapid mix to the flocculator, from the flocculator to the sedimentation basin, those arrows are all within my control volume. So when I'm actually doing a mass balance, I wouldn't even consider those. Just to give you kind of a sense of mass balance. Now, the reaction we're looking at is aluminum sulfate, and sulfate, the aluminum sulfate has 14 waters of hydration. So water of hydration, you can think of a chemical, if you dry that chemical in an oven, it's very, very difficult to remove. You're not going to remove those 14 water molecules that are associated with each molecule of aluminum sulfate. So they're associated with it. If you kind of think about if you took Jell-O and you made a Jell-O and you left the Jell-O out in the air, it's really hard to dewater Jell-O. Okay, and it's because essentially you've got water molecules that are associated with the gelatin. So alum reacts and it forms 2 moles of aluminum hydroxide, and aluminum hydroxide has 3 waters of hydration. This is a solid. So we're going to add alum and will form aluminum hydroxide. I haven't balanced the equation. I will subsequently, but for now we don't need. What we need to know is how much we've added and how much aluminum hydroxide we produce, because what we're asking for is how much sludge is produced. So we added 12.5 milligrams per liter of alum. The molecular weight of alum, and that includes the waters of hydration, is 594 milligrams per millimole, and that is equal to 2.1 times 10 to the minus 2 millimoles. Now, the stoichiometric ratio for aluminum hydroxide to alum is 2 to 1. So that means for every 1 mole of alum we add, we produce 2 moles of aluminum hydroxide. So in terms of aluminum hydroxide, we produce 4.2 times 10 to the minus 2 millimolar. So this is the amount of aluminum hydroxide precipitate that we would produce. So that's the amount of solid. And we're assuming here that we actually have exceeded the solubility. So we're assuming we're precipitating all of that. We're going to multiply that by the molecular weight of the aluminum hydroxide. Again, remember you need to include the waters of hydration in calculating the molecular weight. And that is 5.5 milligrams per liter. To calculate the mass of the solids, we have 5.5 milligrams per liter. We're treating 0.5 cubic meters per second of water. There are 86,400 seconds per day. It's a number that's actually useful to remember. And there are 10 to the minus 6 kilograms per milligram. And that is equal to 239 kilograms per day. So we would produce about 240 kilograms per day of solids just from precipitating the alum that we added. In terms of suspended solids, we also want to remove those. We had here 87 milligrams per liter, and we have 0.7 milligrams per liter leaving. So remember, again, you're looking at your mass balance through this system. So we have 87 minus 0.7 milligrams per liter. Again, we have 0.5 cubic meters per second. There are still 86,400 seconds in a day, and there are still 10 to the minus 6 kilograms per milligram, and this is 3,728 kilograms per day. So the total mass we produce is 239 plus 3,728. It's almost 4,000 kilograms per day of solid. Any questions? So what we've done is we've calculated this is the dry weight of solids that we would produce. Now when we add alum, and this is the full reaction, So we add alum. That releases aluminum ions, sulfate, and 14 waters. And it's these aluminum ions that react with the colloids to neutralize the surface charge, to destabilize the colloidal suspension, and to form flux. If we have sufficient alkalinity present, then what happens is these aluminum ions can also react with bicarbonate. And alkalinity in fresh waters is equal to my bicarbonate concentration plus 2 times my carbonate concentration plus my OH minus concentration minus H plus. And here your concentrations are in molar units. So, and in fresh waters, having a pH of around 6 to 8, your alkalinity is approximately equal to your bicarbonate concentration. And that's because the hydroxide and hydronium concentrations are small, as is the carbonate. So those concentrations are all much smaller than the bicarbonate, so we can say that the alkalinity is approximately equal to the bicarbonate. And here what happens then, if your aluminum ions react with bicarbonate, you produce the aluminum hydroxide that we talked about, and CO2, and the system is buffered. And if the system is buffered, what does that mean in terms of pH? So if you have a well-buffered system, what does that mean in terms of pH? So a solution with a high alkalinity is well buffered. That means that that water is able to resist a change in pH upon the addition of an acid. If it's alkalinity, when we talk about acidity, it's upon the addition of a base. So a buffered solution, again, is one that is able to resist pH change upon the addition of an acid or a base. So if you have sufficient alkalinity, you're not going to have significant changes in the pH of that water. If you have insufficient alkalinity, then what you produce is sulfuric acid, and you will have a significant decrease in the pH. So you'll have trouble controlling the pH of the system. And in a drinking water system, you don't want significant changes in the pH of your treated water because you end up with corrosion problems. We'll do this part of the problem, and then I think I'll just stop and ask questions because I don't want to start the alkalinity part. So if we have a sludge solids content, so that sludge that we're producing, that we calculated that we had roughly 4,000 kilograms, you don't produce dry sludge. You produce sludge that has a high concentration of water. And then you want to remove that water before you transport and dispose of the sludge. So we have a sludge content of 1%. That means that that sludge that you're producing is 99% water and 1% solids. So it is 1% solids and 99% water. Mostly water. The specific gravity of the sludge solids, of the actual solid itself, particles itself, is 3.01. And you're asked, what is the volume of sludge? Okay, so we produced, the dry weight that we produced was 3,968, almost 4,000 kilograms per day. We need to know the specific gravity of the sludge. And since it is 1% solids, the specific gravity of the sludge is simply weighted specific gravity of your solids and water. And water has a specific gravity of 1. So the specific gravity of the sludge is 1.02. The fraction of solids is simply the mass of my solids divided by the mass of the solids plus the water. That's the only thing we have. We're going to assume we have. And this is equal to 0.01 because we said we had 1% solids. And this is equal to 3,968 over 3,968 plus the mass of the water. And if we do the math, we calculate a mass of the water is equal to 39280. So we have almost 400,000 kilograms of water in this sludge. So the volume is equal to the total mass, so the 3,968, so the mass of the solids, plus the mass of the water, times the specific gravity that we calculated here, times the density of water, which we'll assume is, we'll just use the 1,000 kilograms per cubic meter. We're multiplying by the density of the sludge, and this gives us 404 cubic meters per day. So we would have roughly 400 cubic meters per day of sludge that we would have to treat and dispose of. So we're 1 minute after. I'll stop there. We'll do the alkalinity calculation on Monday, first thing, and then we'll move on to rapid mix basins.